Good morning, everybody. My name is Gavin Wooler from ETAS, and I'm going to be your host and moderator today for this discussion. The discussion is the top critical mistakes in developing automotive software functions on microcontrollers. Automotive software functions in modern vehicles are highly important. In automotive systems, microcontrollers play a pivotal role within ECUs, managing essential functions ranging from engine performance to safety features. Despite the expertise of developers, errors in software development can significantly impact product performance and reliability. Today, I have a few experts next to me, and our experts will be addressing common mistakes and their consequences, touching on practical examples. Please be aware that due to the time limitation we have, we will not be able to really go into full detail on every mistake, but nevertheless, we're going to give you a very good insight on what our expertise is in that area and how we think you should be controlling this. So let me introduce my colleagues here from ETAS next to me. To my right, I have Zoran Coutura. He's a technical acquisition manager for business development in the ADAS AD middleware solutions at ETAS. He joined in 2019 and has more than 25 years of experience in the automotive industry, working in and managing projects with OEMs around the globe. Welcome, Zoran. Next to Zoran, I have Dr. Frederik Stumpf. He's the head of ETAS Cybersecurity Solutions. Frederik's been with us since 2013. He's an author and a co-author of numerous publications on the topic of cybersecurity, and he's worked in various cybersecurity research institutes like the TU Darmstadt, TU München or Fraunhofer, and for many years now within the automotive industry, such as Bosch and ETAS, of course, as well. And last but not least, Nigel Tracy, the Vice President of ETAS RTA Solutions. Nigel joined in 2003, worked in various areas like telecommunications, avionics, and automotive, resulting in over 30 years of experience in deeply embedded, real-time, and safety-critical systems.
Thanks.
Welcome, gents.
Thank you.
Okay, then I would say we'll start, due to the time, with the first topic, and that is overlooking cybersecurity. So, failing to implement robust security measures, leaving systems vulnerable to cyber threats, cybersecurity has become increasingly important within the automotive software, especially in the context of SDV. Here, I'd say that everything should now start with cybersecurity to make your microcontrollers future-proof. So, what are the risks of overlooking cybersecurity microcontroller-based systems, and how can this be mitigated?
Yeah, thank you, Gavin, for this question. Well, actually, let me start off with automotive industry. We are actually seeing that over the past 2 decades, 3 decades, that the complexity in EA architectures and in in-vehicle networks is continuously growing. There's new network protocols being introduced, and these are also introducing new vulnerabilities to the systems and to these overall setups in the vehicles. And considering that with these introductions of connectivity to the networks, even outside the vehicle, we now have assassins around the globe being able to remotely access the vehicles and actually take control of different systems in the vehicle, actually, and introducing different faults and problems in there. So this is really a severe problem that we're facing in the automotive industry, and it must be addressed with according measures during the development. And Frederik, I think you're the far better expert to explain that and go into more depth.
Thank you for the nice overview. So absolutely correct. So we are seeing currently 3 major trends in SDV vehicles. Its first one is, as you already pointed out, so we have new E architectures. And these new E architectures, we use more and more vehicle computers, so computers with more processing power. The second trend we are currently seeing is we are using more and more general purpose operating system inside the car, and they make use of open source software components, which have a lot of vulnerabilities also due to the big code base. And last but not least, we are seeing that the vehicles are more and more connected to the outside world, so making wireless capabilities, but also integrating mobile phones and stuff like that. And all these 3 trends, so they cause that we have a bigger attack surface as in the past, right? And based on these three trends you're seeing, there's a lot of or different classes of attacks you can try to misuse these different capabilities, ranging from remote controlling the vehicle. And this is often the infotainment system, which is the entry door for that, because you make use of vulnerabilities in the software. You try to overtake the infotainment system and then inject safety messages on the vehicle bus. And there's a couple of attacks you find out on the globe on various vehicles in this current class. The second trend we are also seeing, as said, is based on chip tuning, right? This is pretty old, but we still see a lot of attacks around chip tuning. So trying to manipulate the engine controller, or even in EV vehicles, also taking care of the controlling devices, which is controlling horsepowers and speed and stuff like that, to also bring some additional horsepowers. And the last one, sorry for that, is you could also try to steal the car by, for example, circumventing immobilizer or remote keyless entry systems. This is also quite often attack which we are currently seeing.
Nigel, you can say something?
Yeah, I think there's also a very important and strong link, as Frederick was just mentioning, between the cybersecurity and being able to ensure safety in the vehicle. I mean, if you can't guarantee that the software that you proved was safe or used processes to show was safe, if you can't prove that hasn't been modified or changed, then of course you have no foundation to make your safety argumentation, which is very important. Also, if the ECUs can be compromised, and we've seen this in practical attacks, then safety messages can be broadcast on the bus and acted on by the other ECUs in the car. So this is a very critical thing for the overall safety architecture of the vehicle. One very common mistake that I've seen made when it comes to cybersecurity is adding it in at the end. So this can often cause big problems, especially when you're adding in capabilities like encryption or authentication of messages, adding in cybersecurity cryptography stacks. These take processing time. And if you add them in at the end, the risk is you find out your system no longer fits within the real-time constraints that we'll talk about a little bit later. And then you have to do a lot of re-architecting and rework. So here, typically, it's much better to build in the cybersecurity software from day one and maybe just use dummy keys, but so that you can understand the overall performance impact on the vehicle from the very beginning.
Yeah. So Nigel, you pointed out a very nice approach, of course, also integrating security from the beginning. What is also important, and here some current standards help, like ISO SAE 21434, is employing a systematic security engineering process. So not only start with security from the beginning, but also employ this complete security engineering process in the complete development lifecycle, and also be prepared for potential vulnerabilities after SOP, so defining also incident response mechanisms, for example. Be embraced for these activities, because there will be vulnerabilities, there will be bugs in the software, and you need to accept them, and you also need to find countermeasures how to deal with them. And especially since the car is a safety system, you also need to cover the implications between security and safety, right? Because an unsecure system is difficult to be safe, right?
Correct.
Okay. And I mean, this also includes using tools, using test setups to scan your vulnerabilities, to scan also for other protocol problems, using, for instance, solutions like our CycleFast solution that will help you, for example, to find implementation problems in your software. And this is just an example of different toolings that can be used in these environments. But it's important to be including that into your test processes and test setups, also to address it accordingly.
And as early as possible.
Exactly.
Good. Then, thank you very much. Let's go to the next one we have in line. It's the ignoring hardware constraints topic. So failing to consider the limitations of the microcontroller, such as memory size, processing power, and available peripherals, can lead to inefficient or non-functional code. So Nigel, to you, why is it crucial to consider hardware constraints like memory size, processing power, and available peripherals when developing automotive software functions?
So I think, Gavin, this is a key topic that actually defines embedded software. By definition, it's embedded into a system that has limited resources, and you've got to fit within those limited resources. Those limited resources are typically, as you said, memory size, so the amount of space for the code, the amount of RAM for the application variables, and the CPU time. And in automotive, this is particularly critical because production volumes are so high. And with high production volumes, obviously, every little bit of resource that you're using pushes up the cost. And if you're producing millions of something, even pushing up the cost by a small amount can have a big impact. But the consequence that this typically has, if you don't consider it from the beginning, is that you start off developing the software and it's all going well. And then as you slowly add more functionality and get closer to the complete system you're targeting, then suddenly you hit a borderline where it no longer fits within the system. And then you're having to restructure or re-architect the system. And that if you follow that approach, the risk is you end up with an iteration causing a lot of rework of work you've already done, a lot of revalidation of work you've already done. And that's especially more complicated when you look to modern microcontrollers with multi-core support. They're actually very complicated internally. So the way memory is placed on the chips, whether it's local to a core, whether it's a global pool of memory, that can have tremendous impact on the performance of accessing that memory. Typically can have an impact of somewhere between 2 and 10 times slower to access different memory pools. And therefore, designing that in from the beginning is also really critical to get the most performance out of the more complex microcontrollers that we see today. Similar with on-chip buses, moving data around the system. They're typically a resource that's shared. And if you don't monitor this carefully, if you don't set up your design carefully, you can end up causing some worst-case execution time behaviors that are hard to test for, hard to notice, but lead to bugs in the field.
Frederick?
Yeah, so absolutely correct what Nigel just stated. So what we also have seen when we introduced a lot of software design concepts or security concepts in hardware limited or resource limited devices like microcontrollers and stuff like that. So we have seen that advanced security components or advanced security concepts, they also consume processing power, right? And the first new security concept when it comes to SDV were, for example, a secure boot or a secure onboard communication. And this causes that you need more processing power for securing the ECU and at the end, then later on the car. And when we introduced some of these concepts in the beginning, we had really big challenges to meet the overall system requirements, being, for example, on bus in 100 milliseconds, which is a typical requirement. And when you now want to employ secure booting mechanisms, you execute some cryptographic features to make sure that the ECU is in trusted state or in a secure state, then you could fail on this requirement. And this is especially problematic when you only have limited hardware resources. The same was true when we introduced secure onboard communication, for example, and first series projects. You've seen that it was completely under-assessed, the complexity behind this concept. And at the end, the ECU was only doing security. You didn't have enough time for the real application. And this also shows that you need to be aware of what your hardware can do, and then you need to come up with pretty good design concept, how you make use of the limitations.
Yeah, maybe even sometimes it would be better to start off with estimating and trying to address what are the software requirements that we are having and what are the implications on the hardware and resources that we're taking there, and then designing and actually acquiring the right hardware devices for the according software functionality that we're intending to create. Which is usually not the case, because what we're ending up usually is we have a designed hardware, we have a hardware EE architecture, and we have to press in our software architecture and software functionality into that devices. And that's basically one of the major challenges in the automotive industry, also in the embedded.
A question into the round, the topic of photo and lifetime updates. How does that influence the hardware limitations?
So it brings in new challenges, of course. If you're going to continue to expand the software over its lifetime, then you also need to make sure that you're leaving some headroom within the available hardware constraints so that you can update the system over its lifetime. Otherwise, you have no room to put anything else in there, and then those photo updates can deliver basically no additional value. And that, of course, is then a trade, because there's cost with leaving that spare capacity.
Yeah, and also often if you're doing the photo update in the wild ride, you also need to consider about safety and reliability, because it could be that you need to back up the old software, right, to make sure that it's still functional. And for this, you need then double the size of memory, right? And otherwise, you would delete it, back up only the bootloader, for example, and this could also cause confusions or later an issue on the road, right? This is why this needs to be covered inside the hardware design or the hardware layout.
Okay, great. Thank you, gents. Next one. Mistake number 3, or challenge number 3, failure to ensure software safety. Very important topic, and hardware and software also need to adhere to safety standards. Frederick, you mentioned one earlier on. We quite often hear about the ISO 26262. Failure to ensure software safety is a critical mistake. So what are the key challenges in ensuring the software safety?
Yeah. Again, like we already said about security, safety is a similar tier here. And it's, I mean, when we're talking about the vehicles, almost every function is kind of safety relevant because, well, it's pretty obvious with chassis control systems like brake systems and steering systems and so on that this is kind of problematic or could be dangerous to the traffic participants and so on. But even with functionalities like headlights, like your instrument cluster, like belt control or whatsoever, these are all potentially dangerous for the vehicle passengers and traffic participants. And so therefore, it's crucial to introduce that in all these functionalities and have an according safety process and safety design in that complete setup, starting from the safety of the intended function, SOTIF, but then also going into the functional safety. And I think it's also clear that with the rising complexity of software that we're introducing into the vehicles, with the higher functionality and complexity also of the EE hardware architectures, microcontrollers with multiple cores being introduced, it's really harder for us to design the software in these concerns accordingly. So I think Nigel.
About to say Nigel.
Yeah, so I think there's two common mistakes that I see being made in the development in the automotive industry. And here, maybe the automotive industry still has some opportunity to learn from other industries like aerospace, like nuclear, like railway, that have a maybe more entrenched, stronger safety culture over many more decades than the automotive industry has. But the two common mistakes that I see is first a thinking, okay, now we need to add safety, so what do we add? And normally adding things is not good for safety. Simple is always good for safety because safety is about reasoning and arguing and understanding the failure modes and conditions the system can get into. So if you find yourself in that mode of thinking, what do we now add for safety? There's a big risk that you might be just heading down the wrong path. The second thing that I see very often is the safety standards like ISO 26262. They prescribe a process to follow for the development of the software. And if you're not careful, that becomes the goal of the development process, to get MCDC coverage of the code. Now, actually, the guidelines or the reasons those things exist in the safety standards are to check that your tests are good quality. So the goal isn't to get safety coverage. The goal is to test the functionality of your software is working correctly, and then to see if your tests are good because they cover the code. But very often I see all of the process steps and all of the documentation steps prescribed by the standard become a goal in their own because they're very measurable. And as engineers, we like measurable things. So we head towards that 100% target, but a little bit mindlessly. I've even seen some projects where the goal is to get code coverage and you're not even checking the outputs. Well, then you're adding no value when it comes to safety. So it's very important, I think, to be careful that the safety standard that you're following doesn't become the goal. It's there to support you building a safe system, but the goal is not to just hit the standard.
So you would say it's more like a framework to set, to partially live by, but also then to watch at all the other areas, like you mentioned.
Absolutely.
And again, there's different tools from different vendors, like also from ETAS, that can help you to design your software accordingly to the measures that are necessary for safe software. Like in ASCII Developer, we're providing different features in order to do that. Also, it's necessary not only to look at the design of the software and how it is being realized, but also how it is being documented and how you can follow up on these parts also. Relating all your implementations, relating all your functionalities and your tests to the according requirements that you have been designing. So it's a thorough requirements engineering process that needs to be set up, and it needs to be supported by according tooling and then an according design process that incorporates with that.
Yeah. But one addition also where you should also be a bit careful is exchanging a safety mechanism with a security mechanism, for example. So there are some examples out there where you try to, for example, take a CRC and say, okay, if CRC has comparable capability as a message authentication code from the security side, right? So you could come to the conclusion, hey, I can spare some resources if I just exchange a CSC with a MAC. And this might work in some circumstances, but in some other, it will not work because you also need to take the overall capability of the hardware into account. For example, if you perform this on a QM device, and it's different than if you perform this on the ASLD device. So there is similarities between safety and security, especially if you look from the process side. So ISO 26262 mentioned has strong similarities to the ISO 21434, which is security standard, especially if you come to threat and risk analysis or the hazard and risk analysis. There are strong similarities, but it's not trivial to just exchange a safety mechanism with security mechanisms. So they can be there to be combined or in addition, but I would not exchange them, right? So this typically will not
needs
work.
both.
It needs
safety
both,
and security. It's not exactly the same.
Correct.
And I think one additional aspect is like the software integration parts that we're looking at. We need to take care of all functionalities that are incorporated and integrated on a single device, that we address the freedom from interference between different modules, different software components, and specifically also concurrencies that are running on one device. Yeah? And I think, Nigel, that's also an additional topic that needs to be addressed in RTA solutions usually. Yeah,
yeah, exactly. I think we'll come to that when we talk about timing, especially, and that has is a whole class of safety failures as well. Yeah.
Okay, great, gents. Frederick, I think it was you mentioning documentation, or Nigel. Nevertheless, again, missing of proper documentation. I think that's one of the pitfalls we quite often see out there in with our customers. And in that respect, poor or non-existent documentation makes it difficult for others, even the original developer, to understand and maintain the code. So good documentation is essential, especially for long-term project success. So Frederick, I'll address this one to you. Can you tell us why and what the risks of poor and non-existent documentation are?
Yeah, thanks, Kevin. So it's very crucial, especially for the long-term success of an automotive software project. And it's not only about the code, but it's also about tool chains, right? How to use the tool chain, but also how concepts are being done, right? And also it becomes extremely relevant because what we also often see is that you are reusing code bases for new ECU generations, for example, right? And now just think of, it's not sufficiently documented. You cannot be sure that at the end the ECU is doing what is planned to be done, or what is standard components if you're not certain how it was developed and how they are documented, right? This is a big challenge. And also if you take into account that team members are leaving, right? So after an ECU project is done, often we have the case that the team, they're migrated to new responsibilities, right? And so no one really in the team knows how software code has been developed. And this is crucial to also document this, also not by the developer alone, but also perform some peer review, for example, that the documentation is readable and stuff like that. So to make sure that the documentation is in a good state and can actually be used also for new activities, but also for the integrator or something like that to make use of the software code.
Nigel?
Yeah, maybe I can just give one concrete example to some of what Frederick was saying there in terms of that longevity, which is especially important in automotive, right? The products we build have a very long life cycle. So a couple of years ago, we got a request from a customer to do an impact assessment because a bug had been found in a compiler, and they wanted to know whether our operating system was impacted by that bug. But the version of the operating system they wanted to know this about was more than 20 years out of production, not just out of development, but 20 years since we were selling it. Now, that requires really good documentation, as Frederick says, not only about the software itself, but the process to check it and to make a release. And that is really important. And one aspect that I think is key to documentation and is a critical mistake is sometimes there's a lot of work on documentation that are write-only documents. A lot of effort is put in documents that people write and nobody ever reads. One of the things I find can add most value to documentation is traceability and linking them together. And that all the way through, ideally, into the code. And ideally with simple tools and scripts and easy ways of tying them together. But that tends to improve the read to write ratio of the document, because there's an awful lot of write-only documents in the software world, I feel.
I think that's right, but on the other side, with also the raising complexity of all the software functionalities in the vehicle and so on, we're also seeing that there's added resources like additional programmers that are joining the teams and need to understand the code and need to get a thorough and further understanding of what is happening actually with that functionality in order to be able to maintain and continuously improve the software also. And that's what's happening also in the future, that we're with FOTA functionality and all these stuff now intending to continuously develop this also further on. And here, again, some tools can be very supportive to help you get a better understanding of your code and understand where to look at also. eHandbook is a very perfect example in my perception there also, because it really tremendously supports you to get a handle on what exactly is happening in the code and how do you have to understand where the signals are and what so on you can address.
Yeah, what we're also often seeing, and a common mistake, is that especially when you run in task force mode, right? So you're at the end of the SOP, and now you need to do everything together. You need to do the development, you need to integrate and test and stuff. And then typically what often an activity is, I document later, right? I now do the code, and then I document when I have more time, right? Often a common mistake is that you don't have time, right? And at the end, you run out without a documentation at the end. And this is also a common mistake. Focus on documentation because it's pretty crucial.
Especially when the workforce changes, like you said earlier on, then you're stuck. And the task force mode no longer helps you to be in that mode because you cannot fulfill what's needed from you.
I find it actually a good habit to start the documentation before doing the implementation usually. And that's what... in many projects we've been seeing with other groups also that are implementing these kind of habits as a crucial settlement in the teams.
And a well set up documentation helps you later on to get to that position, to that point you want to look up very much quicker than having just a pile of pieces of paper or files lying around spread out across the system, because you will not be able to find what you're looking for.
Exactly. As Nigel also pointed out, it also helps for a lot of certification, like the ISO, for example. You need a very good requirements tracing documentation, and it will only be more cost intensive at the end when you want to go for a specific certification or qualification, and you need to redocument it, then again, it just becomes more expensive.
Yeah, I think it's anyone who's been in the industry for more than a very short amount of time knows it's never better in the future. You never have more time. So it's very tempting to think, as Frederick says, we'll fill in the blanks. We'll catch up and tidy this up later. But normally pressures are only increasing. There's never a lull.
Great. So thank you on the documentation topic. The next one is the inadequate timing control. So many microcontroller applications have real-time constraints. Ignoring these can lead to missing deadlines and system failures. Developers must ensure that their code meets the timing requirements of the application. So Nigel, I will address this to you first. So based on real-time constraints, could you explain to our audience what real-time is in this context and what the challenges are?
Yeah, sure. Let me try. So I think this is an area where there's still an awful lot of misconceptions and wrong ideas. So first and most important, real time is not real fast. It doesn't mean performance. It doesn't mean needing to write efficient code. Of course, typically you do need to write efficient code because we talked about the resource constraints. But real time to me is simply one thing. If a result is late, it's wrong. Just like if the wrong value was calculated, well, if the result arrives late, it's wrong. And to show that's not equivalent to being fast, let me give a very simple example. The Y2K bug is a good example. The year 2000 was pretty much coming for 2,000 years, but it was a very hard real-time deadline. If you hadn't fixed and corrected systems by this date, then you missed the deadline, the system would fail. And that's important definition of real time, because what it means is in the system that you're building, average case performance isn't important. What's important is the system must still meet the deadline, even in the worst case. And that means you need to work a little bit different. You need to look at performance in a little bit a different way to try to look for that worst case behavior, for those worst case paths. And a lot of techniques that are used in general software development to improve performance aren't valid or relevant anymore, including a lot of hardware mechanisms. You know, you have hardware mechanisms like caches, like branch prediction, like speculative execution. These are tremendous at improving average case performance. But if none of the data is in the cache, You want to make sure your airbag's still getting fired on time. Therefore, you care about worst case performance. And that's a very common mistake, not to make this mindset shift that real time is all about ensuring deadlines. And deadlines means even in the worst case, the system's got to work. And there you've got a tension with what we talked about earlier with the hardware constraints. Because if it's got to work in the worst case, you want to try and make sure those worst cases are not so far away from the average case. Otherwise, you're having to overspec the hardware. So that it can still function in the worst case. And so much of what is done in an embedded control system is real time. So just as Zora mentioned earlier, that so much of what's done safety relevant, so much of what software does in the car, because it's controlling hydromechanical electrical systems, is real time.
Can you share some insights on how to effectively monitor and control timing during the development process?
So it's a combination of three things, I would say. So first, you need to design things. So looking typically at the event chains in the system from stimulus to response and understanding what are the deadlines on those is the first step, because that's where the real-time requirements come from. The second step is then to design carefully the scheduling of the system to make sure even in the worst case, as the system has to do many things in pseudo parallel, that it can satisfy those requirements on those event chains. So looking at things like what priority to run tasks at, where to control preemption, where to allow preemption, that's an important part of the design process. And then last and just as important is then to find ways to measure the worst case execution time of the blocks of code so that the analysis or the design you did in the middle phase is valid, that you know that the code, even in the worst case, is only taking so many CPU cycles so that it all fits together.
And just as you mentioned, the designing of all these deadlines and run times, it's also necessary to address the jitters and the latencies that can happen within the actual time control and within the actual execution of all your functionalities. So you cannot always guarantee that in these microcontroller setups, you will exactly have that same execution because of exactly the preemptions and different situations being able to happen in this concern. So it's something that you need to think through very thoroughly and very clearly also address it in your complete systems requirements and systems engineering.
Maybe to Frederick, from a cybersecurity point of view, microcontrollers, real time, how does that?
It's of course a challenge because when you're introducing, and I shortly explained also when we arrived on this hardware constraints topic, that there are cybersecurity concepts or mechanisms you need to employ which have an impact on timing control, like secure onboard communication mentioned already, right? So it needs processing time to apply message authentication codes to onboard messages, for example, right? So this consumes performance time and also might have an impact on the overall timing of the ECU. And this is also pretty relevant so that you, when have these requirements, that you also take the complete use cases into account. What is the use case you want to implement? What is the requirements you want to implement and realize? And then later on come up with sufficient design concept how you deal with these different requirements, especially regarding real-time capabilities.
Nigel?
Yeah, I think building on that as well, I think obviously typically the systems we build today at their very foundation have a real-time operating system, something like an AUTOSAR operating system. And just as Frederick pointed out there, it's very important to take account of the cybersecurity overheads of running those algorithms. Also, your operating system introduces overheads. There's task switching times, there's interrupt latencies. You need to factor those in, which means you need a real-time operating system where those things are known and documented, because you maybe don't have access to all of the information to determine that on your own, but that's an important part of the overall end-to-end latency from stimulus to response. As an interrupt is being processed, tasks are being started, they're being preempted, and then you're generating an output. So there you really also need support from your real-time operating system by documenting those things like task switching time, interrupt latency.
And so it's a very big topic, even though it looks so trivial, the real time, but there's so many things to look out for. Let's go to the next one. I'm sure we will have a chance potentially later on as well to cover more of this. Insufficient testing. So insufficient testing, especially under different conditions and over longer periods, can result in unreliable software. But how does insufficient testing impact software reliability? So on.
That's a very good question. Well, just like with documentation and with some of the other aspects, what we've said already, testing is not something that you can postpone to a later point in time in the project. You shouldn't be addressing, and we've seen it so often. Yeah, it's like people are thinking of, let me just do that implementation now, and I will do the test later, or somebody else can do the tests for me. And it's actually, I would consider that developers need to address a big amount of their actual work into testing and put testing to a very high priority and importance in this concern also. Because exactly this is the case when you postpone that or neglect it in this case, then you will see all these failures introduced into your software designs, into your current architectures, only rising up later on in the project. And then you'll have to change your architecture again and change your implementations overly again. And this is really something hard to address when you come back to a thing that you've implemented 6 months ago to say, like, I need to change that and understand that now. And this is really one of the biggest problems I'd consider in insufficient testing also. And then there's so many disciplines around testing, starting from unit and module testing, going to then integration testing, cybersecurity testing, vulnerabilities, and so on. So this is really something that should be addressed from minute one, starting directly with your processes, starting with an engineering process that introduces and integrates your testing capabilities and abilities directly, making it a test-driven design.
Yeah, what we're also seeing quite often, right, is that a lot of tests are only to test against a specific specification, right? So you test the compatibility to APIs, you test compatibility of components to the specification. But what is also quite important is to make sure to test against irregular use of the software components. We call this more or less fuzzing, right? So here, more or less, you try to generate test cases also based on random data and test and check how the component, the ECU or the software component, is behaving after providing random test data, especially when then you cause that the ECU is rebooting or stuff like that, or suddenly in an interrupt mode. You test and validate then what behaves then, what is the measures you're seeing then, and then you try to equip again the device with additional test cases, for example. And this is quite important to also make sure that you're not only testing in the specification, because also, as said already, but also make sure that you are also making sure that you are testing against irregular use of the component.
I think that's a very important part. I think, Nigel, you earlier on had a topic of, that's your, let's say, your set script on the basis of which I do, for example, now here the testing. But in end effect, the irregular use, how often do I know somebody's handling something within the vehicle and that's not the way it's supposed to be handled, but you've got to take that into consideration. So very important part on that respect as well.
Yeah, absolutely. And especially for topics around safety and cybersecurity, then that's typically where those failure conditions or vulnerabilities come into the system. So, and I think when you're looking at testing overall, one important mistake that I see often made is not looking at it holistically in the overall picture of the development process. So whole classes of errors that can be picked up with testing can also be picked up with other tools, static analysis tools, or using model-based development and code generators. So for example, as Zora mentioned earlier, with Ascot and its code generator, you can generate correct fixed point arithmetic without overflow, without underflow. That eliminates whole classes of testing that you would otherwise have to do by using tools. Using static analysis tools can eliminate whole classes of things that you would often find with testing. And I think the other thing that's really important and often mistaken is you lose sight of the purpose and the goal of testing, and the process of testing becomes a means in its ends. And I mentioned that before with the safety standards, and it's very often around this testing area that instead of testing the system to see that it's performing correctly, you're trying to get your code coverage metric hit. And that's a big mistake that I see, that is spending a lot of time. You know, the real purpose of code coverage is as a quality test of your tests, not as a goal for your tests. I mean, it should raise the question, if I don't get to 100% coverage in the code when I do my requirements-based testing, why? Not simply to go fill the gaps blindly and just get to that 100%.
And then again, testing is such an important aspect in that overall engineering process, but it is also a very costly, and sometimes it's requiring us also to think about measures to make testing a more affordable task and something that we can actually integrate into our day-to-day work. And therefore, also virtualization in this context is a very important solution and resolution to these cost aspects. We've seen many tests being done in the vehicles or on HIL systems, but going further into fully virtualized systems that can solely be executed on your PC devices or even being distributed into cloud setups is something that is tremendously improving these aspects and helping you to continuously do your tests.
But you will still need the real-life testing at the end of line testing, etc. Because virtually, yeah, that's fine. You can cut out a lot of costs in that respect if you can cover everything. But in the end, real life, getting into the vehicle, doing tests is still needed.
But that's right. But you can already reach a certain level of reliability on the software levels, and then going into the vehicles and addressing the right amount of tests.
Focusing then.
Finding software errors in the vehicle is very expensive. You should be finding them quite a lot earlier.
Great. Okay, great. Thank you very much on that one. And let's go to the last topic we have on our agenda today, the lack of effective automation. So let's briefly talk about the lack of effective automation. Insufficient and ineffective automation of recurring integration, testing, and deployment activities creates a high demand for resources. Nigel, please elaborate on this one.
Yeah, I mean, this ought to be a topic that we're excellent at, right? Because we're full of people who can write code and can solve problems with scripts. And yet it's something that maybe we don't focus on enough. This can sometimes be because we give the boring jobs to the most junior developers. And then they see this as their task just to do it. But the mindset here should always be, if you do a job twice, automate it so you never do it again. If you do a job third time, you failed somewhere along the line. And that can be across the whole process, from executing the process for building the software, to running your tests, to checking your traceability and your completeness of your requirements traceability into your tests or into your code. All of those steps are automatable. And we've got all the skills in our teams to do that, because we're full of software developers in here. So we ought to be much better at this. And I've often found that an effective way of doing this is give some of the boring jobs to the best and most experienced engineers, because you know what? They hate it, and they won't do it 3 times, I can tell you. They very often won't do it twice. And there can be a false economy to moving some of the boring, repetitive jobs to somewhere where you think you're taking cost out. But actually, you should be eliminating the jobs completely. You should be automating them so that they're then just execution time.
That also includes some of aspects that are going beyond continuous integration and continuous testing tasks, because these are very obvious to all of our developers' tasks. But looking into open source software scanning, looking into documentation aspects of our releases, looking into different other aspects that need to be integrated and that are really repetitive tasks that are recurring on every release. This is something that needs to be automated, in my opinion, and that's where we often recognize the teams are not thinking far enough ahead of this the processes. It's really most important, in my opinion, to take focus on automating as much as possible everything that is recurring, so that you can focus later on doing the creative tasks of implementing, planning your actual code improvements and implementations. And that's really, as Nigel just mentioned, sometimes it's best to address that to the best engineers.
And on a fractious moment, you mentioned virtualization to the mistake beforehand, so I presume a brief insight on that one.
It's absolutely right. Like especially on the testing tasks, on the continuous testing, like your virtualization can help you to improve these testing tasks tremendously, because you can more easier actually execute your tests in an environment that is not hardware bound and so on, especially on the functional levels. Some timing tasks and so on can probably only be tested in accordance with the right hardware setup and so on. So you need to distribute the right tests to the right system setups, and virtualization can be an improvement to your testing setups very strongly also.
Fredrik?
Yeah, you also mentioned CI/CD pipelines, right? So they are a very nice instrument to do this. But what you also should be covering with these CI/CD pipelines is your supply chain, right? Because currently it's not only that you focus on your own code, but you also make use of more complex code also from suppliers, for example, right? And you need to be prepared that there will also be updates in the software from the supplier, right? So there will be bugs, there will be vulnerabilities, right? This you need to integrate. And what is often the false strategy is to just focus on your own code and then only irregularly take software supply chains or the components from the supplier into your pipeline, and then this could also cause some errors or problems, right? So embrace for this and make sure that all your CI/CD pipelines also cover, of course, the complete supply chain.
Good. Jens, then we covered 7, I think it was in the end, 7 critical mistakes that we see when we are out there in the market. Yeah, thank you very much for answering those. I say we now go across to questions. So thank you first of all to everybody who's listened in. We will now start the Q&A part on this. And we have already received a few, and let's see how this goes along. And I will read it from up front of me. So again, feel free. I'm not going to point it out to anybody specific in this case. Let's start with the first one. What should good documentation of testing and safety critical embedded applications look like?
So I think here, obviously, the process standards do give some guidance on what's expected, because you've got to make your case, you've got to make your argumentation potentially to an external body. Even if you're not going through a certification process, you at least need to be happy that you have complied with the requirements coming from the safety norms here. One thing I think is very good practice here is not to overcomplicate things, though. So as I mentioned before, I think the key to good documentation, and that's true whether it's helping you with functional development, but it's even more true when it comes to safety critical features of the software you're building, is traceability. It's linking things together. It's linking from that safety requirement and from that failure mode into the part of the code that's helping to implement that, or into the test that's showing that it's able to detect those failure modes and handle them appropriately. And there, keeping the documentation relatively simple technical-wise in tool form, that helps you do things like parse it with simple scripts and pull out tags that you can use to link things together. Because with things like code, there's no easy mechanism in order to trace into code. But you can do that with smart comments and tags, and then just create simple Ruby scripts and things like this to link things together. So I always think it's important, of course, to follow the requirements that are coming and expected to show that you have met the requirements coming from the safety norms, but also keeping it simple so that you can automate things, you can do traceability, I think is important.
Okay, thank you, Nigel. Next question. I'm currently working on the topic of cybersecurity testing. This question is very basic. So when I speak about cybersecurity testing, I perform tests like static analysis and fuzz testing on a C code. What exactly I look for? Do I look for some buffer overflows and memory outbound errors, or check that the secure boot and cryptographic functionalities are working properly? Fredrik, that's your area.
So this is a very good question, and also not so trivial to answer, right? So in easy words, you need to do both. So first of all, of course, with cybersecurity testing, you try to find vulnerabilities in the software, like detecting buffer overflows. Fuzzing can help here. Also, there's also other tooling which can help here. Static analysis is named here, right? So this is the one approach you're doing. But on the other hand, you also need to make sure, of course, that the cryptographic functionalities and the test cases are generated in a way that you can test all the capabilities of the cryptographic function. So on the one hand side, as said already, making sure that the software is secure, so no buffer overflows, but on the other hand side, also making sure that the functionality is working as expected and according to specification.
Okay, thank you. Let's get to the next one. which is the way to go for future MBSE, i.e. system model with Simulink models integrated into tools like Rhapsody or hand coding?
So at least let me take a start, and then Zora, maybe you want to add on this one. So I think there's different types of software that you need to create to solve the problem, and trying to force one approach for everything might be maybe our eighth mistake here. So parts of the system that you're building are real-time control systems that are effectively implementing control algorithms. So either PID loops or differential equations are being implemented. For those things, model-based development tools make a lot of sense, because the people who really understand that are the control engineers, not the software engineers. And they'll do a better job working at it in a language and a methodology that they understand, with model-based development helping them focus on the controls. But other parts of the system are about state management, about decision making. And as a computer scientist, I always think those things look terribly clumsy in a model-based development tool compared to writing them in code directly, much more readable in code directly. So I think using the right thing for the right part of the system and not thinking you can build the whole system in one fixed way leads to better quality, using the right tool for the job, basically.
There's not much to add to what you said, but just around the hand code or towards hand code, I think it's obvious that more in the field where we're using more data handling and working with bigger bigger chunks of data, like with video inputs or what so on. This is something that needs to be addressed in a different way, and it's usually not as easily handled in model-based software engineering. Yeah. So therefore, I'd consider this something to depending on the type of software that you're creating and the type of functionality that's desired, and what kind of data you are actually looking at. Though the tools are also now providing a lot of interfaces to address video, radar signals, or what's on in the model-based software engineering designs. So I think it's probably also a question of taste of the coding developers.
Yeah, I think that, as I mentioned before, I think the code generators with model-based development, code generators like the one in Asker, can eliminate whole classes of errors in things that even very good human programmers make mistakes on, because it's boring, repetitive work. Implementing fixed point arithmetic to get the mathematical precision you need with the performance you need, that's really boring, hard work. But a code generator doesn't make those mistakes.
Yep. Okay. Good. Next one. For virtualization. I expect that virtualization would make the cost higher, because at the end, we will do the full testing again on hardware, so we only added a new layer of testing. Is it okay from cost perspective to do this vs the issue that we might find, keeping consideration that most problems happens from hardware, software working together?
It's always a consideration that you need to take, like, does it actually save me efforts, time, money, or does it add additional time and money to the process to do this kind of a virtualization? The target of virtualization usually is to replace at least a portion of your hardware-based tests and push them to an earlier phase in your development. And it's very important to address this shift left of testing, because the earlier you can address failures made in your development and design process, the better, the less cost it will take. Does virtualization resolve everything in that? No, absolutely not. So you need to think through it, and will that kind of virtualization help you to actually maintain a better process in this concern? So it's never a black or white answer.
Yeah. Nigel?
Yeah, I think just adding on that, over the last 50 years, there's been plenty of empirical studies in computer science that shows the cost of fixing a bug grows exponentially from its point of introduction to its point of fixing. So even though I wouldn't necessarily agree with the premise in the question that you need to repeat all of the tests, as Zoran just said, even if you did, finding the bug earlier and fixing it closer to when you made it, it's still understandable at that point because it's not so long since you introduced it. You've still got good knowledge of that part of the code, and B, the amount of rework that needs to be done. So it adds tremendous value even then. So the studies show somewhere up to 2 orders of magnitude more expensive if you're finding a bug than in the final release of the product or in the field compared to finding it when you're doing testing during the development phase. So
plus, I mean, you said you cannot do just the one or the other. You have to do the proper testing, so that not the virtualization, but the real life testing. But in effect, like you said too, you will find early enough mistakes in a surrounding and an environment which sort of tries to reflect your real life environment. And then you can run through your later tests much quicker because so many mistakes, errors might not crop up at that point of view. So again, both of them don't take as long as you only do one of them.
Yeah, absolutely. And I absolutely would never trust or feel comfortable with a safety critical system that had never been tested in the real hardware, in the real environment. Yep. But that doesn't mean that virtualization is just adding a cost. What it's trying to do is make sure that you find only those errors that can be found in the hardware environment there, and that the others you're finding much earlier and fixing much cheaper.
And especially experiences that you've made in the field, experiences that you have kind of learned in your later processes, you can also pull into your virtualization environments and make sure that in the future, once you're releasing something from your virtual setups, is going to be robust against problems that can be introduced in the hardware setups again. It will never release these hardware-based testings though, but in the end, it's something that can tremendously increase your speed and lower the feedback cycles to your developer.
Okay, we'll do one more.
Okay.
One more. Let's see how long that takes. Which real-time operating system do you recommend for safety-critical ECUs or applications?
Okay, so responsible for a team that creates a real-time operating system maybe makes me a little biased here, but let me try to abstract it away from the details a little bit. So in the automotive industry, if we're talking about real-time safety-critical, then we're really talking about an AUTOSAR operating system, especially if we're talking, as we are this morning, on microcontrollers. I mentioned some of the things that I think are important here for coming from the operating system when we talked about timing behavior earlier. So if you want to use a real-time operating system, it needs to provide you with certain information, like how long it takes to switch between tasks, how long the interrupt latencies are in the worst case. Because, as I mentioned, you care about worst-case performance. So these are the kind of things that I believe are important to look for when selecting and sourcing a real-time operating system. Of course, we also spoke earlier about resource constraints. So it needs to be small as well, needs to be small and fast, because you don't buy your hardware to run a real-time operating system. You buy it to run the HVAC, to lift the window up, to run the engine. And therefore, you want as much of that resource for the real value-adding functionality as possible. And last but not least, it's a little bit connected to both, but you want the worst case performance to be the focus in that operating system and to be optimized. And ideally, the worst case, the average case, and the best case are very close together in the way that operating system has been implemented. And that kind of information should be available if someone is claiming they're building and selling a real-time operating system but can't provide you with that data. Then the question is, well, what makes it real-time?
Okay, great. So I'm sorry to say the time's up. It's been great talking to you, and hopefully, I'm sure for most of you viewing today, you found mistakes we've brought up, which definitely aren't all of them, but we've brought up here, that where you can reflect and say, I've experienced those, I've seen those, and that we're able to give you some advice, some help in the direction of which way you should be working. If you've recognized some of them, but we haven't then covered certain other ones that weren't here mentioned, then please use this chance and get into touch with us. Talk to us. We're happy to help you to find solutions to the mistakes you think you're doing or which you are seeing. And approach us, come towards us and get into touch. That would be my call to action for you as well here. And on that basis, again, from my side, a big thank you to all of you. Looking forward, keep on track with our webinars, because this was the first one in a row of numerous ones, and have a look on the various channels in social media and on the webpage, of course, as well. So thank you very much.
Thanks a lot, and happy coding.
Thank you. Have a great day, everybody. Bye.